My name is Cameron Bennett, and today I'm going to be going over the sample problems on the website. So first of all, we want to understand why we're doing this problem and why it's important. Understanding pedigrees is important as they show how human traits are passed through families, and they allow us to have a better understanding of the heritability of traits for diseases and non-disease traits. In particular, I chose this problem focusing on redheads and heritability because, as you can see, I am a redhead, but I am also the only redhead in my family in living memory. So I've always been pretty interested in where my hair came from and how relatively rare recessive traits actually are. Alright, so let's get started on this pedigree. First of all, something we should look at is the colored in individuals are individuals who have the trait we're looking at. So in this case, red hair. So because we know that red hair is a recessive trait, we know that anyone who has red hair is automatically going to be a 2 small r allele. So we can go in and fill that in really quick. And then I like to work bottom up and then top to bottom once I kind of get into the middle. So going from the bottom, let's start with this individual. We see that they have two little r's. So we both know that they had to get a little r from both of their parents. So put that there. But we know that both of their parents, neither of them have red hair, so they both have to be heterozygous, big R, little r. So we can also tell that because this person also has a descendant with this hair color, we can kind of trace it up this way. So we know that this person likely got this little r trait from their parent. So we can go kind of that way. And then this rule kind of applies looking backward up. So now that we have this parent had to give all of their kids a little r. So this is one of their children has a little r. This one of their children has a little r. That one we already put, and this one has a little r. But then looking at it again, none of their direct children have red hair. So then we can go in and add the big R to all of those because we know they're heterozygous because they don't have the trait expressed. So now we can go over to this side. And we know that this parent is not affected, but we can't guarantee that they don't already have that trait. So we're going to put it as big R and then a gap. And this is the same thing for this parent over here, big R and a gap. So now coming back over here, we know that this individual had to get a little r from both parents. So we can put it like that. This one, we know definitely has at least one big R, but we don't know what the other one is. It could be a little r, it could be a big R, so we have to put it as a no idea. Going back over here, we know that both of these offspring had to have a little r, so this one gets a little r as well. And then both of these kids don't have the trait, but we can't guarantee what they got, so they're going to be a little r, big R dash. And then this parent, we also don't know what they have, so we have to say big R dash. And then going back over to this side of the table, we know that this parent, we don't know what trait they have. So we know they definitely have a big allele, but we can't say for the little one. And then both of these kids are also going to be kind of our unknowns because we know that they definitely inherited a big R from both parents, but we don't know if any of them are heterozygous or not. So we have to leave them as they definitely have a big allele, but we don't know about the other one. And then last but not least, we don't know about this parent, but we know that this kid definitely does not have the allele, so we can say big R and hold off. So this is how we do that problem. For the second part of this problem, we're looking at a cross between individual 3-3, which is a homozygous recessive individual, being crossed with a heterozygous individual. So we see this individual crossed with this individual. So because this particular trait is a Mendelian recessive trait, we can cross it in a Punnett square. So we're going to make a nice little Punnett square. We have R, 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 and then we can just fill them in. And as we can see, 2 out of 4 have the trait, while the other half of them are going to be carriers. So we can say that there is a 50% chance. So the third part of this problem is our most complicated because it utilizes the binomial expansion equation. So particularly we're looking at, given the scenario of having 5 children, what is the probability of having 2 girls, both of which are redheaded? So I chose this particular scenario because most of our studies focused on or found that women with red hair are going to be the most likely to have complications with anesthesia. So I wanted to look at the probability of somebody who is going to have kids who are going to be affected by this medical complication. So starting off, we need to determine our probability of everything that's not a redheaded girl. So we're going to start with our probability of a redheaded boy, our probability of a non-redheaded boy, and the probability of a non-redheaded girl. So each one of these we can calculate pretty simply. So the odds of having a redheaded child based off of these parents in this cross is 50%, so it's 1/2. And then because you can either be a boy or a girl, that is also 1/2. And because it's the and, we multiply. This is the same for all of our other scenarios right here. So the odds of having a non-redheaded boy in this category is 1/2, and then the odds of it being a boy is also 1/2, and the same applies for the girls, non-redheaded girls. So each of these is 0.25, 0.25, and 0.25. So then we sum up all of these non-scenarios, and we get 0.75. So that tells us that the probability of having a girl who is redheaded is going to be 0.25. So now we plug all these into our binomial expansion. So starting, we know that they're going to have 5 kids. So we're going to have 5 factorial over the probability of 2 girls and 3 boys, and each of these are factorial as well. Then we're going to multiply this by the probability of having girls with red hair, 0.25, to the power of how many times this is going to happen, so 2 in this scenario. And then this is going to be multiplied by our probability of not having a redheaded girl, which is 0.75, to the power of 3, which is how many would be in this scenario. So this is kind of tricky math, so we're going to plug this into our calculator, and we're going to get a result of 0.264. So 0.264 is the probability of these parents having 5, given that they have 5 children, 3 of them will be boys, 3 of them will not be girls with red hair, and 2 of them will be girls with red hair. All right, thank you.